Ready? Okay, so our next speaker is Dave Wagner.
Thank you. So this is a talk about generalizations of the Howman-Lieb theorem from the point of view of finding regions that are free of phase transitions. So the Li-Yang theory of phase transitions. And I'm fortunate that all of that has been explained already in talks of Alan and Roberto and Jason and Klaas. So I'll take that as more or less given. And anyway, I'll give details when we come to it. So it's a general class of, well, you could call them models, but I have nothing in particular in mind to model. I'm not claiming any physical significance. These are just things that you can build coming from graphs. But I'm going to sort of interpret them quasi-physically. So I've got a big finite graph. It can be any graph at all at this stage. But, you know, Avogadro's number of vertices. I'm going to be interested in the set of all spanning subgraphs. So I might as well think of it as given by a set of edges, and implicitly all of the vertices of the graph will be in my subgraph. And what do I want to know about a spanning subgraph? Well, the number of edges, certainly. The degree function is a bit more informative. So I'm going to record the degree of every vertex in this spanning subgraph. And it's useful to let v sub k of h be the set of vertices of degree k. So that's just a bit of notation. So what I'm going to do is associate an energy to every spanning subgraph, kind of using kind of standard things. Every edge will have some particular energy associated to it, and every vertex will have a particular energy if it's a vertex of degree k. This is like a chemical potential of a vertex of degree k.
Can you run back one slide? You went real fast. dk.
Yeah, so it's just a set of vertices where the degree of that vertex in the subgraph is k. So there are k edges in the set H incident with the vertex V. Yep.
G is allowed to have multiple edges.
Yeah, G is totally arbitrary, but it has to be a graph.
You have to have any vertices?
No, the theory is uninteresting, but.
When you are saying spanning, this H is spanning, so it suggests you consider connected.
No, that's not necessary.
Now, for a graph theory, spanning just means that the vertex set of the subgraph is all of V. Edges don't have to touch every vertex.
Right. So the vertices are all there, and you might have no edges at all. That's actually going to be the zero temperature.
Spanning.
That's spanning, right. It's just not connected. So the language is different. Okay, so to every spanning subgraph then, or I'm just going to stop saying spanning. For every subgraph, this is what I'm going to define to be the energy. And I was using H for the subgraph and E for the edges, so U for energy. So for every edge, for each of the edges, you get an energy J. For each vertex of degree K, you get an energy mu K. And the sum of all these contributions is just what I'm going to call the energy of the subgraph. So we've got a configuration space of all the subgraphs and an energy function on that space, and you plug that into the usual Boltzmann-Gibbs machine. Give it an absolute temperature. There's the inverse temperature. There's the Boltzmann weight. And there's the partition function, according to the standard recipe. So I'm interested in zeros of this partition function because of the interpretation in the Li-Yang theory. As accumulation points of these zeros, if you have a sequence of graphs, accumulation points on the positive real axis in certain variables is indicative of a phase transition. Is there a question?
The ordinary Ising model is a special case of this.
Not the Ising model. The matching polynomial will be a special case of this.
The high temperature graphs of the Ising model will be a special case of this, because those are Eulerian graphs.
Yes, but there's an extra contribution coming from, I should have backed up and said, in my energy function, I really would like to add a term proportional to the number of connected components. but I don't know how to handle that in the theorems that I'm going to show you.
In the high temperature expansion of the Ising model, that doesn't matter.
Okay, so I can get the high temperature expansion, asymptotically at least, I guess. Okay, so I'd like to write this partition function as a polynomial in something, so you make this standard change of variables and write it as a polynomial. I'm going to call the U's activities. I don't know if that's consonant with physics usage, but I have to call them something. So I'm thinking of this as a polynomial in one variable y, which is tracking the number of edges, and a bunch of positive real parameters, or could be non-negative real parameters, the activities, which are basically recording what's allowed to happen at every vertex. So at every vertex, you're going to take u sub the degree of that vertex, and take the product of all of those over all the vertices. That's giving you a weight associated to the subgraph H. And so I'm taking the generating function of all subgraphs, keeping track of the number of edges, and weighted according to the activities of all the vertices. I'll give you a special case of this in a moment. But there's a multivariate version that's important because my proofs involve the multivariate version, although the conclusions concern the univariate specialization mostly. So instead of having one variable for all of the edges, I'm going to have a different variable for each of the vertices and form this monomial here. And then just using the fact that the sum of the degrees of the vertices is half the number of edges.
Wait, I'm sorry. I'm a little...
Yeah?
The x's live on the vertices or on the edges?
X's live on the vertices. And now look what happens if I plug in y to the minus half in here. I get y to the minus half the degree of v summed over all vertices. That's y to the half the sum of the degrees. And half the sum of the degrees is the number of edges.
I see. So you don't put edge weights, but you distribute the edge weights onto the two vertices.
Right.
And then you let those be arbitrary.
Yes. I could have edge.
You also add a non-negative edge weight.
You could have a different weight on every edge as well, actually. As long as they're positive or real, that won't affect one of my theorems. And if they're complex of modulus 1, it won't affect my other two theorems.
So, just so that relating, are these exactly these polymer gases that we were talking about before, or are they?
No.
No.
This is
No, it's much more general.
They included as a special case.
Yes, but maybe not keeping track of the same information. Let me give you an example. I think that's what's coming up next. Yeah. Okay, so here's a special case. Suppose the activities are 1 at vertices of degree 0 and 1, and 0 otherwise. So this monomial that's attached to every subgraph is either 1 or 0. It's 1 if all of the degrees of the vertices are 0 and 1, and it's 0 if any vertex has degree at least 2. So this is an indicator that says it's 1 if my subgraph is a matching and 0 otherwise. And so these are precisely the multivariate and the univariate versions of the matching polynomial.
if you put u0 and u1 equals 0 and u2 equals 1, then you have loops.
That's right. Then you have the generating function for all fully packed loop configurations. Okay, in the proof that I'm going to show you, the vertices actually end up decoupling from each other completely. So there's no need to put the same chemical potentials at every vertex. You can put different chemical potentials at every vertex entirely independently. So every vertex gets associated a vector of activities, and you redefine this weight of a spanning subgraph just by the usual thing. At vertex V, you use the associated vertex weights, depending on the degrees there. And then you've got the multivariate partition function just the same. Okay, so that is the setup. That's the thing that I want to talk about. And here's the main result. The hypothesis is phrased in terms of these polynomials. So it's a local hypothesis. You just have to look at every vertex separately and you form what's essentially a generating function for the vertex activities at that vertex. This k goes from 0 to d. These are the possible degrees that the vertex v could have. If it's got degree k, this is the activity associated with vertex v having degree k. And the d choose k's in this, well, they're an artifact of the proof. They come in because they come in the proof. So you form these polynomials at every vertex. And, well, I guess I'll say it now. It's important to notice that the activities do depend on the temperature, because the chemical potentials you think of as being fixed beforehand, and then these activities are e to the minus beta, the potential. So if you want to apply this hypothesis to find phase transitions, it's important to realize that these polynomials depend on temperature, except when they don't. And they don't depend on temperature if your activities are either 0 or 1. And what that means is that the potentials are either infinity or 0. And that just means that the degree, the vertex v having degree k is either permissible or impermissible. So there's no energetics involved at all. It's just permissible or impermissible. And then it's not temperature dependent. So that, in a sense, makes the 0-1 case of these activities a little nicer to work with, but not essential.
It's usually, in physics, it's usually come from the limit temperature going to 0.
Yeah, that's
along two different directions, and this gives you some weight to, there are permissive configuration.
Yeah, certainly in the higher low temperature limit, these are going to be there's going to be negligible or non-negligible terms, and that's the same as the 0-1 limit. Yeah. But in the middle range of temperatures, there might be some range of activities. Okay, so here's the theorem. You start with an assumption on the zeros of all the key polynomials associated to each vertex. Assume that they're all close to the negative real axis. All the zeros are within an angle of alpha of the negative real axis. Two conclusions then. If all of the vertex variables are close to the positive real axis, then the multivariate partition function doesn't vanish, which is exactly the kind of thing you want for absence of phase transitions. And when you do the univariate specialization, you get to double that angle because of the y to the 1/2. Now the nice thing is that this statement is independent of the size of the graph, so you can take thermodynamic limits, and this is still a zero-free region for, so this region will be free of singularities of the limit of the logarithm of something. Well,
So this shows, if all you care about is the positive real axis, this shows absence of phase transition in the entire physical region, provided your keys all the zeros of all your keys lie in the left half plane with a little extra epsilon of angle.
right. Now, the difficulty with that is that the keys are temperature dependent, and temperature is one way of parameterizing the positive real axis.
Oh, by the way, there are, let me just say left half plane, because there are finitely many keys. You've got a finite graph. So
yes.
if the zeros of all the keys lie in the open left half plane, then you will get some tiny sector around the positive real axis.
Right.
That's zero free.
Right. So here's the picture. You assume all of the key zeros are there, and assume that there are only finitely many keys that come up. Then, if all of the values of the x variables are in this sector in the right half plane, it's just related by right angles to this one, then the multivariate partition function is not 0. And then if you substitute all of the x's by y 1/2, you get to double the size of that sector here. So think about what happens if this green sector here shrinks down to the negative real axis. Then this red sector expands up to the right half plane. So that's the case when alpha is 0. if all of the zeros of all of the keys are non-positive real numbers, then the half-plane property holds for the multivariate generated function, and all of the zeros of the univariate generated function are non-positive real numbers. So that's the alpha equals 0, special case of the first theorem. So the Heilman-Lieb theorem is applying this to the matching polynomial. U0 and U1 are equal to 1. All the other UKs are 0. There's only one, there are, the key polynomial at vertex V is 1 plus dz, where d is the degree. So if your graphs have bounded degree, there's only finitely many of these keys appear. In any case, for a finite graph, the multivariate matching polynomial has the half-plane property, and the univariate matching polynomial has all its zeros on the non-positive real axis. So that's a very simple special case. There's no reason to take all of the activities the same at every vertex. If we change them vertex by vertex, just say pick two numbers, f and g, that differ by at most 1. Or pick a range of degrees that's either 1 or 2 consecutive numbers. And say the activity is 1 at vertex V if the degree is either f or g. So you've got 1 or 2 permissible degrees at every vertex, and they're adjacent. Then you get exactly the same conclusion because all of the keys are just, some power of z times a linear term with positive coefficients. So you get exactly the same conclusion. Half-plane property for the multivariate generated function and only real zeros for the univariate one. So I proved this even before I met Alan. But this one I would never have dreamed of. So you can sort of take this game one step further. Suppose I allow degrees 0, 1, and 2, but all other vertex degrees are impermissible. Then this is the key polynomial, and you just hit it with the quadratic formula, which is still one of my favorite things to use. And you find all of the zeros are within pi over 4 of the negative real axis. So you apply this theorem. If all of the zeros of if all of the x's are within pi over 4 of the positive real axis, the multivariate generated function doesn't vanish. And if all of the zeros are within pi over 2 of the, if y is within pi over 2 of the positive real axis, then this doesn't vanish either, the univariate one. So Ruel proved something a little bit stronger in 99, namely, you're allowed to have real part not too small, right? It's minus 1 over a cubic in the maximum degree of the graph. Now, if I allow myself to say something about the maximum degree of the graph here, I think I could bump this over to pi over 2 plus a little bit, depending on maximum degree. So that would be.
But your method naturally gives you sectors, and you get no control whatsoever over the magnitude of x or y. Is that right?
Those are my other two theorems.
Yeah, but in this theorem.
In this theorem, it's just about argument, right?
What is Ruel's interpretation?
Yeah, he doesn't give one. He submitted it to a combinatorics journal. I think because he couldn't find good physics interpretation for this.
If there's one other case of interest to physics, which is the simplest case is Eulerian graphs. So the UK is 1 if k is even and 0 if it's odd. Mm-hmm. Or more generally, put a magnetic field. So UK is 1 if k is even, and some number t if k is odd. Mm-hmm. Can you say something for that? Because that will include the Li-Yang theorem translated to high temperature graphs, if you can handle that.
I've thought about it, but I can't get the Li-Yang theorem this way. I can get some zero-free regions at extremely high or extremely low temperature, so it's just what you would expect. This is really kind of a qualitative or semi-qualitative, semi-quantitative at best, because it doesn't really see the graph structure. For instance, in this theory, I can't tell the difference between the hexagonal lattice and 3 space, the cubical lattice in 3 space. They're both graphs of degree 6 regular graphs. That's all that this theory sees about the graph.
So what you are saying that if I have Young zeros on the circle, so you can prove that there is this wedge at high temperatures where it doesn't close?
I'm not sure that's what I can say. I don't know if I can say anything about Lee-Yang zeros, honestly. I'd like to think about it. I mean, I have thought a little bit about it. Maybe for a 4 regular graph I can say something. Okay, so that first theorem was about argument. I've got 2 kind of complementary theorems about modulus. If all of the zeros of all of the keys have modulus at least kappa, then you've got vanishing inside a small disk. And usually kappa is less than 1, so this is a much smaller disk. And in the other direction as well. If all of the zeros have modulus at most kappa, then you've got vanishing outside of a large disk, and kappa is, in this case, typically larger than 1, so that you've got non-vanishing outside of a much, much larger disk. There's a caveat here that you have to also assume that the degree of every key is equal to the degree of the corresponding vertex. And the reason for that is that this theorem and this theorem are essentially related by x goes to 1 over x. And that's just a necessary thing. So these 2 theorems have a nice corollary. If all of the zeros of all of the keys are exactly on the unit disk, then the same is true for the well, in fact, there's a multivariate statement that specializes to this. If all of the zeros of all the keys are on the unit circle, then the same is true for the univariate generating function. And a simple case where you can apply that gives you this strange-looking statement. So you sum over all spanning subgraphs, keep track of the number of edges, and then weight each spanning subgraph by the product over all the vertices, the reciprocal of the degree in the graph, choose the degree in the subgraph. All of the zeros are on the unit circle.
Oh, that's because the key is just 1 plus x squared plus 1.
Yeah, exactly. The key is tuned so that you get the hypothesis here for free. So those are the analytic statements. What about thermodynamic limits? So suppose I've got a sequence of graphs whose union is an infinite graph gamma, and well, just for simplicity, each graph is regular. All of the vertices have the same degree. And here, I really want to emphasize that the keys, these polynomials, do depend on temperature or inverse temperature. And I'll just assume that this thermodynamic limit exists. I don't know what you would have to put into the theory to guarantee that, but I know that people here know how to do that. Then, if you have a point, if you have an inverse temperature at which this free energy is non-analytic, then at that temperature, the key has to have a 0 that's not at the origin and has non-negative real part. So this gives you a really nice test for, a very simple test for non-analyticity of these free energies. So for example, let's look at the situation in Ruel's theorem. The permissible degrees are 0, 1, and 2, but it's a bit more general now because I've got arbitrary activities on degree 1 and degree 2 vertices. Whoops. So you can see if U1 is not 0, if it's positive, then all of the zeros of this will have they'll have negative real part. They'll either be both on the negative real axis, or they'll be complex conjugate with negative real part. So if that's the case, then you won't have any phase transitions. But if U1 does equal 0, in which case you're looking at subgraphs where every vertex has degree 0 or 2. So these are loop configurations that aren't fully packed, I guess. Then you get this temperature bound. If the temperature is low enough compared to the energies of the chemical activity and the edge energy, then there's no phase transition at low temperature, which is exactly what you would expect. But there's a quantitative version. So here's another simple application. It gives you a kind of a qualitative theorem. At every vertex, fix up to 4 consecutive degrees. And I'm going to say that the activity of a vertex V is 1 if K is in this range from F to G. And F and G aren't too far apart. You can pick up to 4 consecutive degrees that are permissible at every vertex. Different at every vertex if you want. Then in the thermodynamic limit, you never get phase transition ever. Oh, it's kind of nice. And last example. So this would handle, I guess, Eulerian subgraphs of a 4 regular graph. I'm allowed vertices of degree 0, of degree d, and of degree 2d. And I've got a 2d regular graph. I'm going to say a vertex of degree 0 and a vertex of degree d are chemically neutral, and a vertex of degree 2d has an activity of u, where u is e to the minus beta mu. Mu is the chemical potential. Well, the nice thing about this key is it's the substitution of z to the power d into a quadratic. And you can use the quadratic formula, which I still like to do. And as long as the discriminant of that quadratic is negative, you'll have a pair of complex conjugate roots, both of which have the same modulus. So by the second and the third theorems that I showed you, all of the zeros of the partition function will have that modulus squared. And that's uniform in the graph. So in the thermodynamic limit, there's only one point that could be a singularity. And you get this bizarre looking statement. If the temperature is sufficiently low compared to the chemical activity of vertex of degree 2d, then there's only one point that could be a phase transition. It's a solution to this horrible looking equation. Now, I toyed with the idea of showing you that first before telling you how you got it, because it's just the quadratic formula. Okay, so in summary, this is a very general setup, but it records absolutely no global structure, which is disappointing. I'd really like to get the number of components of the subgraph in there somehow, but I don't know how to do it. Also, it sees absolutely nothing about the ambient graph except the degree of each vertex. So it can't tell the difference between a hexagonal lattice and z cubed with nearest neighbors. So I'd like to be able to put in some global structure power series as well to tell me something about the graph. I mean, it's something that records the number of cycles of given lengths in the ambient graph. On the other hand, it unifies a number of previously known things. Heilmann-Lieb, some things of myself, of Ruel. It's got very mild hypotheses, but it's also got reasonably mild conclusions about absence of phase transitions. Lots of soft results, some quantitative hard versions of intuitive results. I would rather say many qualitative results and some quantitative results. I mean, because they're all comparable difficulty, and saying that these results are hard kind of might suggest that they're difficult to prove. They're not.
Yeah, but hard here doesn't mean difficult.
I know, but
Hard means like hard analysis as compared to soft analysis.
Yeah, I would rather say qualitative and quantitative.
That's what I'm saying.
Yeah. And the proofs, there's really only one technique that you need in addition to what Alan talked about regarding Heilmann-Lieb last week. Yeah, you start with the half-plane property of something that obviously has the half-plane property. And then this step here, you polarize some things and you apply the Grace-Walsh-Segu theorem. Monkey business is just some trick for introducing the activities into the thing, and then you diagonalize. So the proofs are short and easy. Well, there are some things I'd like to do with this, but I don't quite know what yet. So for instance, on the hexagonal lattice, if you look at the zero temperature thing where edges are expensive, the ground state is just the empty subgraph. And if you raise the temperature a little bit, the lowest energy excitations look a lot like hard hexagons. But then at higher temperatures, you get entropically a bunch of stuff, and these hard hexagons dissolve, and it just becomes a totally different phase, I think. So I'd like to investigate the phase structure of some of these models. And that's it.
Some idea of the proof?
Well, you start with this polynomial, the product over all the edges, and I'll say the edge, yeah. You start with this expression for the sum over all subgraphs, just x to the power the degree of that subgraph. And the idea is that this clearly has the half-plane property. If the real part of xv and the real part of xw are positive, then this is not a negative real number, so this factor doesn't vanish. So if all of the xv's have positive real part, this doesn't vanish. And this is the generating function we want, except we don't have the activities here. So we need to find some way of introducing the activities. And the way that's done is to take each of the variables xv separately, and xv occurs in this polynomial perhaps to the power the degree of v. So you polarize it by replacing each xv by a symmetric function of, well, replacing xv to the power k by the kth elementary symmetric function of d new variables. And then the monkey business comes in. You use the key polynomials in order to perturb that using the roots of the key polynomials, and then you collapse all of those auxiliary variables back to the original xv's, and magically out comes this thing with the weights introduced. That's essentially the proof, but of course it doesn't make much sense. I'm giving a seminar next week, right here in this very room. I'll do the proof, but unfortunately many of you won't be here.
Is it equivalent to not polarize, but just use Hadamard-Scheer composition of two polynomials? Or you might call freshman multiplication of polynomials. You have a polynomial sum of ak z to the k, and another polynomial sum of bk z to the k, and the composition is sum of ak bk z to the k.
I hadn't thought of it that way, but I think, yeah, in some sense this is just at every vertex I'm applying some theorem from one variable complex analysis that says something about the zeros of the Hadamard-Scheer composition of a product of two polynomials. Yes, that's right. And that kind of stuff goes back to early 20th century at least, Takagi and Wiesner and Schur. Yeah.